All right, welcome back to Loving the Physics with Mr. Goldthorpe. So now we're moving on to the second phase or stage of this unit. We're going to talk about waves. But before we talk about waves, let's just do a little review from lesson 1. Remember, what's the source of every wave in existence? And it is some form of vibration. And that vibration creates energy. And that energy then travels through some kind of a medium. And that is called the wave. That transmission of energy through the medium. And also very important to remember, I'll just use a different color here. Remember, the frequency never changes once it leaves the source. So the frequency is determined by the source, and it never changes. Good. And here's kind of an advanced note, which I'll kind of emphasize in an upcoming animation. I'll just kind of highlight it here. If you have a regular source vibration, so if that vibration is in simple harmonic motion, then it turns out the particles in the medium will also move in simple harmonic motion. So that's how it relates to what we've been doing so far. You'll see that there will be simple harmonic motion in the waves itself. So it continues into the medium. Good. Okay, now, in general, there's actually two different kinds of waves out there. There's two different waves in general. The first one's what we call a mechanical wave. So I'm going to highlight that, if you don't mind. I'm going to get rid of this part here. Let me just highlight this idea of a mechanical wave. Now, a mechanical wave has to travel through matter. So that would be like a wave you put through a spring. That would be the medium. Or through water. And even sound waves. Sound waves, if you know, don't exist in a vacuum. So they need matter to even exist. So those are what we call mechanical waves. They need a mechanical medium to travel through. Now the other kind of wave is called electromagnetic. And those ones are dealt within physics 30. Okay, those ones can actually travel through a vacuum. Things like light waves, X-rays, ultraviolet, visible light, radio waves, whatever it might be. So we do those in physics 30. So you don't have to know about those in physics 20. As stated right here, that we only deal with mechanical waves in this course, and they require a medium. And it turns out there are two kinds of mechanical waves. There's the transverse wave, and the key idea for a transverse wave is the idea of perpendicular. Now I'll be showing you this in a second, but here your hand moves up and down, and the wave moves to the right, perpendicular to each other. Whereas longitudinal, the key word will be parallel, where your source moves back and forth, and then the wave goes parallel to that. How about I show you that first? Okay, let's go to, this one requires some videos, there's no doubt about it. So let's move over to the videos and see these kind of waves in action. Let's do longitudinal versus transverse. Okay, so we start with the longitudinal. Remember, I don't know about you guys, that voice scared the crap out of me. Okay, it's a very deep voice. Okay, so those are the two different kinds of mechanical waves. Good. Okay, now let's talk about our first mechanical wave. I just want to see where I have it. There it is, transverse waves. Okay, let's go into transverse waves in detail here. So here I'm just going to select, this is in an animation area, and I'm just going to, let's see how I can get over here. Let's go to transverse waves. Just click on that. Yeah, feel free to click. There we go. And there's our transverse wave. So this is the medium. Could be a spring, could be a rope, whatever it might be. Yeah, and so we're going to, do you guys remember what's the source of every wave in existence? That is a vibration. So we're going to, there's the vibration on the left-hand side, and that's going to be creating this transverse wave. Notice that the vibration is going straight up and down on the y-axis, and the wave is moving along the x-axis, perpendicular to it. That's a transverse wave. And notice that every particle actually is moving up and down. Every particle is moving perpendicular to the wave motion. And all these particles are going in simple harmonic motion. Really cool. So the top of the wave is called the crest, whereas the bottom of a wave is called the trough. In the middle there, we call that the equilibrium location. Basically what it would like if there was no wave. The distance from equilibrium to the top of the wave is called the amplitude, and also the distance to the very bottom of the wave to equilibrium is the amplitude. Good. We're going to get this thing moving again. I just want to show you one more thing. Let's see how my coordination is. Okay, there we go. If we start at the beginning and go right to the end, you'll see that we have one complete cycle of a wave. The length of that would be called the wavelength. That's the length of one wave. Now I'm going to change the amplitude of the wave to little a, like half the amplitude. Do you have any idea what that would look like if it was half the amplitude? Well, here we go. So this is half the amplitude, half the distance from equilibrium to the top or bottom of the wave. Now if I go to triple, watch what happens if I go to triple the amplitude. And this is actually more energy per wave, 3 times the amplitude. Good, so that's the amplitude of a transverse wave. Next thing we're going to do is we're going to go from low frequency to high frequency. What do you guys think will happen if we go to a high frequency source? Okay, this is moving at a higher frequency, more cycles per second. How did you do? Now what I want to do is I want to compare the wavelengths in both cases. So let's start with low frequency. And I just wanted to show you one more time the wavelength of this. Stop it here. Notice that the entire screen is the wavelength. Did you see what happened to the wavelength when I went to high? So here goes to high, and this is going to test my coordination a little bit. See how I do? Not too good. Let's try that again. All right, pretty good. Do you notice how the wavelength now is only half the screen? It's half the wavelength. So wavelength decreased by a half. We doubled the frequency and halved the wavelength, like an inverse relationship. Finally, there's one more thing I want to show you. Just make sure I stop it at the beginning here. Good. Again, notice that on either end, they are one wavelength apart, the two ends. Now watch how the two ends move. Can you see how the two ends are basically moving identically to each other? We call that in phase. So when they are one wavelength apart, they move in phase with each other. Good. There we go. That's a transverse wave. All right, let's go back to our notes now. A lot of diagrams there. And let's talk about a transverse wave. So let's see if we can remember. So do you remember what's the source of every wave in existence? Answer, a vibration. So on the left-hand side here, let's introduce the vibration. And this vibration will be going in simple harmonic motion, up and down, constant amplitude all the way through. And the vibration is going to basically create the energy that transmits through the medium. And you'll notice that the wave here is actually moving, for example, towards the right. That's the motion of the wave. And notice they are perpendicular to each other. The particles are moving vertically. The motion is horizontal. They are perpendicular to each other, so we call that a transverse wave. Key idea, and I'll just use a different color here. They're moving perpendicular to each other. Good. Okay, let's do some more identification here. What's the top of a wave called? Well, that's called a crest. And the bottom of a wave is called a trough. The midline, going all the way along the middle, we call that the equilibrium location. And understand that that's where the particles actually want to be. They don't want to be at the crest or trough. They want to be along equilibrium. Keep that in mind for the future. Do you remember what the amplitude is? From where to where? And again, from equilibrium to the top of a crest, for example, that would be called the amplitude. And from an equilibrium to the bottom of a trough, that's also called the amplitude. And if it's an ideal wave, that amplitude never changes all the way through, if it's ideal. Finally, can you identify the wavelength from where to where? Well, we just need to be able to do the length of one cycle. So if we start here at the top of a wave at one crest, if we go to the next crest, the next successive crest, then you'll see that we've actually done one full cycle here. So from there to there, that would be called the length of one cycle, the wavelength, and we use the letter lambda for that. That's the wavelength. But you know, you don't actually have to go from there to there. There's other options. You could also have started, let's say, here. And if you go from here and then you do one full cycle, then that would be one wavelength. That's lambda as well. So as long as you do one full cycle, the length of one cycle is called the wavelength. Good. All right. Let's try a bit of an activity here. This one's pretty tough, you guys. So it's going to be a little challenging. Do the best you possibly can. Now these are going to be transverse waves. And in the first diagram, you see the wave is going to the right. I want you to tell me what the direction will be of each object, particle's acceleration instantaneously. Which way is it going? Give it a try. Pause. Think about it. Now it turns out this is actually very much like simple harmonic motion. They want to be at equilibrium. That's where they want to be. They do not want to be displaced from equilibrium. So if we take a look at the one on the left, we know that that one is going to experience a force, let's say like a spring force, for example, downward to bring it back to equilibrium. It's called a restoring force. So that would be the direction of its acceleration. Similar for the other ones, that the force will go back to equilibrium, and therefore that's the acceleration. And again, here's the acceleration of this one. They want to go back to equilibrium. So that's how you determine the acceleration direction. So that one's a bit more straightforward because it's very much like simple harmonic motion. But this one is our hardest. It is, how do you find the direction of their velocities? Pause, give it a try. Okay, I'm going to show you there's actually two ways you can solve this question. So the first one is basically saying what's coming towards the particle. Okay. So if we look at the first particle, let's call it particle 1. What's coming towards it? Well, you'll see that there's a crest coming towards that particle. And you have to realize that when the crest comes towards it, it's going to lift that particle up. So therefore, this particle will be moving upward. So that's the direction of its velocity, upward, because the crest is going to lift it upward. For the next one, you'll see that there's a trough coming towards the particle. And if that's the case, then it's going to cause this thing to drop. So therefore the velocity goes down. And if you understand, the next particle is actually one wavelength, again, if I kind of label it, let's label this as 3. 1 and 3 are both one wavelength apart. They are in phase with each other. They will move identically. So this one will also go upward, identically to 1. So this is called what's coming towards it. It's a nice quick way of doing it. Now if that does not make sense to you, then here's another way of doing it. I'll just erase this. And the next one is drawing the wave 1 moment later. So if this thing actually moved to the right 1 moment later, it would kind of look like this. It's pretty hard to draw. Why did I have to draw so many of these? Okay. Anyways, can you see this thing is actually shifted to the right a little bit? Now remember, this is a transverse wave. The particles have to move perpendicular to the wave motion. The dotted line is where the particles are now. So you can see for particle number 1, you see the particle now is above it. So it is up here now. That means it must have moved upward. Like that. And if you look at the next one, you'll see that the particle is now below it. So it must have moved downward to get to there. And similarly for the third one. V is going upward. So you could draw a shifted version of that wave, and you see that where the particle will now be. Either technique is good. So remember, the other technique was what's coming towards it. I'll just show you that they're consistent. The first one had a crest coming towards it. That's going to lift it up. The second one had a trough coming towards it, and that's going to cause it to fall. Done. You see how they're consistent with each other. Okay, that's probably enough for one of these little lessons. I'll see you in the next part.